All right, let's get right into it. We're talking about one of the boldest experiments humanity has ever pulled off, NASA's DART mission. The plan itself seemed pretty straightforward, but the results? Whoa. They sent a ripple effect not just through an asteroid, but kind of through the whole solar system. I mean, at its heart, that's really what this was all about. It was like a giant cosmic game of pool. Think about it. Back in 2022, we sent a spacecraft on this long journey, and its whole job was to just smash into an asteroid. And it was all to answer this one huge question. Could we actually do it? Could we physically move an asteroid? Well, the answer was a big, loud yes. But, that's not even the most interesting part. The mission didn't just succeed. It kind of overachieved. Big time. The push it gave was bigger than expected, the change was greater, and honestly, the consequences were way more profound than any of the computer models thought they would be. And that right there is the big question we're tackling today. How did this happen? Because this was never just about moving one little rock. We're going to break down exactly how this one collision managed to mess with the physics of an entire system. Okay, so first things first, let's start with what is probably the most shocking discovery to come out of all of this. It's something that goes way, way beyond what they were even trying to do. Okay, look at this number, 11.7 microns per second. It seems impossibly tiny, right? I mean, that's slower than a snail's pace. But here's the kicker, and this is huge. That's not the speed change for the asteroid we hit. No. That is the change in speed for the entire system, both asteroids, as they orbit the sun. And that right there is the real headline. I mean, let this sink in. For the very first time in history, humanity has measurably changed how something orbits the sun. We didn't just play billiards with an asteroid. We actually tweaked its entire solar orbit. That's a first. So, how in the world did we get here? To really get it, we need to rewind a bit. Let's look at what the original plan was and, who the main characters were in this cosmic story.
So the basic tech here is something called a kinetic impactor. It sounds super technical, right? But the idea is actually dead simple. You hit something and you hit it hard enough to move it. That's it. And the DART mission, this was the first time we'd ever tried this idea out for real, in space, as a way to defend our planet.
All right, so who was the target? It wasn't just one asteroid, it was actually a pair. You've got the big one, Didymos, and then you have this little moonlet orbiting out called Dimorphos. And that little one, Dimorphos, was our target. The thinking was pretty clever, right? By hitting the smaller moon, it would be way easier to see and measure how its orbit changed around the bigger one. It was basically the perfect setup, like a natural lab in space. And man, did they nail it. The mission was executed just perfectly. The DART spacecraft, screaming through space at something like 22,500 kilometers an hour, scored a perfect bullseye on Dimorphos. And the results? They were pretty much instant, and they were absolutely jaw-dropping.
So before the big event, scientists knew Dimorphos' orbit like the back of their hand. It took exactly 11 hours and 55 minutes for it to circle around Didymos. That was our starting point, our before picture.
And then, bam, the collision. So after things calmed down a bit, astronomers pointed all their telescopes back at it and took new measurements. The after picture, the new orbit was down to 11 hours and 23 minutes. So do the math. That's a 33-minute change. The mission's minimum goal, what they were hoping for, was maybe just a few minutes. So yeah, this completely shattered all expectations. We knew the kinetic impactor idea worked, but the new mystery was, why did it work so ridiculously well? And this is where we get to the secret sauce. The reason this whole thing was so successful. It turns out it wasn't just about the brute force of the impact. Nope, something else was going on, something that gave that push a massive, massive boost.
Scientists have a technical term for it, momentum enhancement, but I just call it the rocket effect. It's way cooler. See, when DART hit, it didn't just dig a hole. It blasted out this enormous cloud of rock and dust, a huge plume of debris, and all that stuff flying off in one direction acted exactly like rocket exhaust, creating a second push in the opposite direction. It basically turned the asteroid into its own little rocket, and that extra kick is what turned a simple nudge into a really powerful shove.
Okay, so this is all really cool science, right? A successful cosmic experiment. But what does it actually mean for us, back here on Earth? Well, in a word, everything. When you boil it all down, it's this simple.
We did it. This is literally the world's first successful test of a planetary defense technology. We proved the whole kinetic impactor idea is solid. And now, thanks to that surprise rocket effect, we know it works even better than we'd hoped. What this means is, if we spot a dangerous asteroid coming our way, say decades from now, a tiny little push from a mission like DART applied early on could be all it takes to make sure it sails safely right by us. And that just leaves us with this really profound idea to chew on. We now have the proven ability to alter the course of the solar system. The DART mission wasn't just about moving a rock. It was about turning a page, starting a whole new chapter for humanity, one where we can actually act as guardians of our own planet. So the question isn't, can we do it anymore? We know we can. The real question is, what do we do next with this incredible new power?